Hello, my name is Chris Gayner. I'm the Director of Labs for Symphony Ventures, and in this video series we're looking to unpack some of the practical realities of intelligent automation, right from process automation up to machine learning. In this video we're going to build on the framework that we offered in the last video around the Digital Operations Toolkit. Just to refresh your memory, it broke up this core framework into three pillars, which was digitization, which is also standardization, optimization, digital labor, which involved process and management of tasks and processes, and digital decisions, which is fundamentally how are we using complex decision making from a digital perspective. The pillar one's all around digitization, standardization, structure, optimization of unstructured data. This is a critical step not only for the data flowing through your business, but equally the interfaces that manage that data, given that around about 80% of data in your organization is most likely unstructured data. Think of texts, chats, emails, phone calls, paper-based data. All of this information is largely unusable from a robotic process automation perspective until it's been some sort of structured format. Alternatively, you can use a very sophisticated machine learning tool to find pattern recognition, to search through these pools of data to actually pick out the information that can then be used by process automation. But equally, it is a very big business case, and the business case is largely unknown until you start getting into that process. Hence why we always lead with the digitization narrative, which is focus on the data and the interfaces going into your business, those core areas that actually drive manual processing across your human workforce, causing your humans to focus more on manual processing rather than value-adding tasks. And actually that's where you can start to drive value from the very front end without looking at digital labor or digital decision making. Getting the digitization element solved first can actually unlock a huge amount of potential for the business. Not only are you digitizing the inputs and the data, actually the outputs of digitization means you have more data, you can analyze this data, and actually you can start to use the data in new and exciting ways. Once the data has been put into a format that is receivable by both the decision-making tools and the labor tools, we have to start thinking about how tasks and processes are managed within the business. This basic XY diagram you're seeing on the screen now offers a really simplistic way to think about where these tools can start to apply in your business. The bottom left of the x-axis is all around dealing with data that is sat somewhere in a data center or information that is historic by nature, sales reports, financial reporting. It is information that, as I said, is historical by nature and thus very static, versus the right-hand side of this diagram, which is all about real-time or data in motion. This is voice. This is information that might be coming through via a stream, so think of like Twitter or other means of information that actually is flowing very quickly and is consumed very quickly, almost consumed at the same time it's produced. The y-axis offers the decision-making capabilities of both humans and robots. The bottom left is the simple decisions, simple by their repeatable, most likely programmable in the sense of a process map, highly repetitive. And if we move to the top of that, this is the opposite of that. This is very judgment-based. This is probably introducing EQ and IQ type decision-making into the framework. Your neurosurgeons will live up the top of this spectrum. Basic yes/no algorithms live at the bottom of this potential map here. Now what we can start to do is start to plot across some of these technologies and find out where their application solves or helps solve problems best. As we mentioned, robotic process automation naturally lives in the bottom left quadrant. It really excels at dealing with static information, simple decision making, where it largely is programmed and defined. As we move away from batch or static data processing, if you're thinking back office processing versus front office decision making, we quickly move from process automation to user interface automation. Think about contact centers and how contact center representatives dealing with a human at one side and all the systems on the other side. They might have 10 to 15 systems open at any one point, which has customer information, product information, information about privacy policies and security information. Having to deal both sides of those things while manage the customer journey becomes very clunky. And actually, if we could have a robot that runs out into the system, the landscape of systems, and pull back the relevant information at the right time, it better guides the agent through a discussion with a client, but equally enables the agent to not have to multitask with the tools and technologies. They can have a better human conversation. We talked about digitization actually driving some of these capabilities. So if we start to think about really basic things around OCR, optical character recognition, when we're scanning documents in, can we initiate processes off the back of those? If we have an interface such as a chatbot or a web form, Equally, can we start to initiate automation off the back of those? And finally, when we start to look at things like real-time voice conversations, again, back in the contact center, do we have tools and capabilities which enable us to better enable those conversations? This, again, is to suggest that digital labor is there not to replace humans, but rather augment humans. I mean, there's a lot of stuff that humans do that machines simply can't get around to, and thus we should look at these as enabling tools rather than replacing tools. Finally, we've dealt with the world of process automation, and just to show you the process map, as everyone has seen, is very simplistic, but is equally very hard to program once we move into very complex arrays of decision making. Humans, as we saw in a couple of videos back, are very good at identifying concepts, patterns, details that a machine needs to be told very explicitly what it is. So this is where we start to move into the world of machine learning. And this is the basic image you're seeing here is a very high level view of how a machine actually starts to learn and can define what it's looking at. I'll give you the 20-second overview for now. There is a lot of detail to this, so I will keep it high level. Thinking about the digitization element, that would fit neatly into the input. So if you're thinking it's a voice, it's a document, it's an email, that will hit the system, and the system then says, okay, I've got something, now I need to normalize it. And this is usually done through a very long series of training and models that are applying here, which is, am I looking at a picture, am I looking at text, am I looking at something else, is it video? The machine fundamentally can't differentiate. It has to understand what it's looking at before it can move into the analysis process. Once it knows what it's dealing with, it then looks at analysis. And if you take text, you're talking about natural language processing, and this is understanding sentiment, intent, criticality and urgency of the words that are on the screen. Equally, it's looking at translation and the words themselves. Image recognition all deals with patterns. Equally, voice and speech recognition, patterns of audio. And again, it's normalizing it into a degree that the machine can understand what it's dealing with. If we take the example of natural language processing, actually we run it through the system. It atomizes all those words in a document. Let's say it's a contract it's trying to read. It atomizes the words and tries to look for things like entities, phraseology, dictionary connections, and through that process, it can come up with a basic level of understanding when it recombines all those words. So it says within this block of text, I know that this is a person talking about their account and they want to do something. There's verbs, there's nouns. I can start to differentiate between those. And from that, it comes up with a score or a prediction around what it thinks the words mean. And so keeping this in mind, the machines aren't thinking. They're very narrow, as we said at the very start, very narrow in what they're doing. They're not actually thinking, they're just processing the information to come up with a confidence level. In the case of a document might flow through, they might be 99% sure it's a document from company A. However, if a picture of a cat comes through, the machine suddenly isn't confident that that's a picture of a cat. They're less confident it's a picture of a document, and therefore the confidence level goes right down. If, however, we wanted to create a machine that could differentiate between cats and dogs, we would have to train the machine on cats and dogs in order for it to identify the patterns that are different between the two. Now, there's two ways to go about training the machine to even come up with that basic understanding. One is human in the loop, and this is if we have an invoice come in and the machine takes a fair stab based on the 1,000 other invoices it's seen, it might identify logos, it might identify the company that is in question, that's the supplier, or it might identify the company that is in has to act on it, which is the company itself, the enterprise. We might, as a human, might say, actually, no, the logo is wrong. It's actually a different company or it's a different supplier. And we can update the system and help train the system there. And the more times we do this, the smarter the system gets at identifying these patterns in what it's being trained. The alternative approach is true machine learning, in which the machine teaches itself to recognize patterns. There's two common ways in which the machine typically does this. One's called through a recurrent neural network. This is by identifying key features, labels, usually from a really large data set. Let's say it's 10,000 images of cats. It can start to identify there is a very common furry triangle in the top left and a very common furry triangle in the top right. There's some whiskers around the middle of the image, and it can start to identify what a cat's face looks like. The other approach is called a generative adversarial network, and this is a very this is a much more robust way of a machine learning it to do itself, in which it uses two machine learning systems. One holds the rules, one holds the goals of what the system is trying to achieve, and the other is largely the player. And these two systems then have a to and fro in which the player tries to figure out the rules of the machine through trial and error. The machine that knows the rules is able to then mark how well the other machine is doing with a reward, or if it gets it wrong, it will punish it. And it's through this really quick and high level of to and fro, it's able to come up with, the player is able to figure out the rules of the machine. And this is all used for specifically around pattern recognition and healthcare, where we don't know what the answer is, but we know what we're trying to get to. And actually, it might come out with some interesting results that we, as a human, could pick up and go and investigate further. Equally, it might land in a dead end in which we have to start again. Super high level view of how these tools start to come together. But as we said, there is the key things to remember is there's a digitization narrative, which is how do you get information into a state that digital labor then can pick up and process, alleviating humans to do more of what we're good at, which is be human. Fundamentally, when we get to a point where actually we could use with some help around decision making, we can start to deploy tools like machine learning to help with pattern recognition, processing speeds, and equally start to look for new areas that we haven't thought of yet. To highlight the machine learning aspect, I've got a super quick video here of anyone's familiar with Super Mario. This is to show you what happens when you unleash a generative adversarial network on a video game, in which this largely is a video game that has taught itself how to play a level of Super Mario. And what you're seeing on screen is the character Super Mario playing a level in which the red line in front of him is actually his prediction score. So he is predicting the best path to complete the level whilst avoiding the bad guys and jumping and doing all that other stuff. Now this is quite interesting, because if you think of what the machine is looking at is zeros and ones, it wouldn't recognize what its character is in this case versus what a bad guy is versus what the sky is. So it didn't go through tens of thousands of iterations to get to this level of efficiency. It went through hundreds of thousands of iterations to know how to move, jump, avoid, speed, and etc., etc., etc. This is just a highlight that actually the model has to learn over and again. So a pure repetition, and actually we can then start to apply this to the enterprise, and I'll talk about that more in the next video. Thank you.